So good evening, everybody, and welcome to October's SecEd evening event. This evening's event has been organised by the SecEd Young Members Subcommittee. Thank you to those of you who joined our AGM, which happened half an hour ago. So for those of you that don't know me, my name is Fiona Hughes. I'm a geotechnical engineer at Arup, and I'm the outgoing chair of the SecEd Young Members Subcommittee, following our AGM earlier. Now sorry, just realised I should probably read this again. Before the presentation, I need to give a couple of housekeeping notes, which are applicable for those of you that are here at the ICE in person. So please could I ask you to take a moment to check that your mobile phone or any other technical device is turned off. Could I also remind you not to leave bags or personal items unattended at any time. In the event of a fire, the alarm will go off and we will leave this meeting room by the emergency exits, which are clearly labelled exit, and we will make our way to Storey's Gate exit. In the event of any other emergency, we will be informed by a member of staff who will provide further instructions. So with the housekeeping done, it's my pleasure to welcome you to this evening's event. And we're fortunate this evening to have two talented young geotechnical engineers presenting on the topic of shallow founded structures on liquefiable layers. I'm going to spend a moment or two introducing our speakers, and we'll then hand over the floor to them. We'll have a Q&A session following both presentations, so please save any questions until the end of the talk. Questions will be able to have questions from here in person, and we also will be able to see questions that are raised online. So please do send in your questions if you're watching online. So to start with, I'll introduce Orestis Adamidis. He's an associate professor of engineering science at the University of Oxford and a tutorial fellow at St Catherine's College. Now, Orestis studied civil engineering at the National Technical University of Athens, specialising in geotechnical engineering. He then moved to the University of Cambridge, where he completed a PhD examining the response of shallow founded structures in the event of earthquake-induced liquefaction. Afterwards, he joined ETH Zurich in Switzerland with a postdoctoral research fellowship. There, his work focused on the importance of co-seismic drainage during liquefaction. Since July 2020, Orestis has been appointed Associate Professor at the Department of Engineering Science at the University of Oxford and Tutorial Fellow at St Catherine's College. His research interests include the response of granular media under partially drained conditions for offshore and seismic onshore applications, the susceptibility of layered deposits to liquefaction, and the interaction between soil and structures during cyclic and dynamic loading. Now, our second speaker this evening, Konstantinos Kassas, postdoctoral researcher at ETH Zurich in Switzerland. Now, Konstantinos graduated from the National Technical University of Athens in 2013 with a diploma in civil engineering. Subsequently, he attended the research-oriented MSc in geotechnical, earthquake, and offshore engineering at the University of Dundee, which he completed in October 2015 with distinction. In 2021, he successfully completed his doctoral studies at the Chair of Geotechnical Engineering, ETH Zurich. Kostas specialises in the field of geotechnical earthquake engineering, focusing on soil structure interaction under liquefied conditions. As part of his doctoral thesis, Konstantinos studied the effect of soil structure interaction on adjacent buildings on liquefied soil. The problem was studied through coupled hydromechanical analyses, modelling nonlinear soil response with the advanced constitutive model PM4 sand, calibrated against soil element tests on Houston sand. Now, thank you both for agreeing to come to present this evening. We really appreciate you spending the time to come to the ICE here this evening to give a presentation. So I'll now hand over the stage to you both. Thank you.
All right, well, thank you very much, Fiona, for the very kind introduction. Thank you to everybody that came here in person, and thank you to the people that might be logged on online to see this presentation. So let's get started. So this is a two-part talk where I will give the first part and Kostas will give the second. We're looking at shallow-founded structures on liquefiable layers. And the first part will focus more on experimental insight, and the second part will be more about numerical insight. Before we start, I would like to thank Professor Madabusi from Cambridge, where the experiments were performed, and Professor Anastasopoulos from ETH Zurich, where the numerical investigation was performed. Right, so let's get started with the first part, which will be focusing more on the experimental insight. Just a brief outline. I will just give an introduction, maybe a bit longer than the second talk about liquefaction and shallow foundations. We will look a bit at the simplified displacement evaluation procedures that we have available, and that will bring us to the main question of this talk, which is what are the mechanics of the problem? What are the mechanisms that govern the generation of displacement? We will briefly go through the methodology, and then we will look at some results that have to do with settlement and rotation for these structures, some evaluation of simplified displacement prediction methodologies, and then we will look in a bit more detail into the deformation mechanisms. Right, so let's get started with liquefaction. I'm sure that most of you will be familiar with it. A conceptual explanation for liquefaction has been available quite early on. So even from the 30s, Casagrande described liquefaction as something that happens in saturated, loose, granular media. Now, these are media that have the tendency to densify when they're agitated, but because of the presence of water, in order for this densification to happen, water needs to leave the pore space, and this cannot happen fast enough. So the water builds up pressure that diminishes the contact forces between some grains, so we get reduced friction, and we can eventually get to a point where the whole deposit behaves like a heavy liquid. Let's see an example of what liquefaction looks like in the field. So this is a video compilation from the 2011 Tohoku earthquake in Japan. So you can see there that we have water coming up to the ground along with liquefied material. Yeah, so it can be quite impressive, but it can also be quite destructive. If we look at where liquefaction happens, because of the conditions that are required for it to be triggered are quite common, so a saturated sand layer, it tends to happen everywhere where earthquakes happen. So these are just some examples from Japan. These are from New Zealand, Indonesia. These are from Greece and Turkey, the United States, and Chile. So everywhere that we have earthquakes. Now, a big part of these failures of the damage has to do with structures on shallow foundations. Now, these photos are not necessarily representative of all the types of damage that we get, but as you might expect, because buildings on shallow foundations are the most common, they form the bulk of the structural stock. So we end up having a large number of them that suffer from liquefaction. And this is only projected to get worse as we have more and more urbanization. So the question for these buildings is, can we anticipate how they behave? We know from earthquakes and from case histories that these buildings respond with increased settlement, rotation. In some cases, we also get sliding. So ideally, in order to design these buildings for liquefaction, which currently is something that is lacking, we need a method to be able to anticipate the displacements that we get, and ideally a simplified method so that it can be used in practice. So what are the methods to evaluate displacement that we have available? Well, in practice, what is often used is simplified one-dimensional methodologies. So methodologies such as Tokimatsu and Sidori, Ishihara, and Yoshimin. So these are based on element testing, and they assume undrained behavior during the earthquake, and all the settlement we get is volumetric. It comes after the earthquake, and the mechanisms that produce it are sedimentation and consolidation. So these are all purely volumetric. Now, it's important to say that this is one-dimensional, so volumetric, and more importantly, these are methodologies that were developed for the free field, not for the presence of structures. So essentially, when we're using these, we're assuming that a structure will settle as much as just the field of a liquefiable layer would, just a layer by itself. Then we have an empirical graph that links normalized settlement on the y-axis, we have S is settlement, dl is the depth of the liquefiable layer. On the x-axis, we have b, the width of the structure, again normalized. And this is data that comes from case histories. It was first proposed by Yoshimi and Tokimatsu, and over the years it was populated with data from many earthquakes until in the late 90s, Liu and Dobry also populated it with some centrifuge tests, and they proposed these thick lines as sort of boundaries of expected settlement. Now, fairly recently, from data collected from the 2010 Maule earthquake in Chile, Berthelot reported some case histories there where we had thinner liquefiable layers, so more shallow layers. And there we have case studies that fall outside of this area. So the question becomes, is this prediction something reliable when we get to more shallow layers? So what happened more recently is that based on these case studies, Berthelot, taking the case studies from Chile and also previous case studies, they proposed a new empirical graph where on the x-axis you have the bearing pressure, the y-axis you have the building width, and they proposed contours that give normalized settlement. So this is supposed to act as an upper bound on settlement. It's not supposed to give you the actual settlement. It's supposed to be the maximum you might expect. More recently, we had a methodology by Bray and Macedo. So there, what they did is they split up the expected settlement into settlement that is volumetric induced, and that can be estimated in an empirical way, similar to the 1D volumetric methodology that we saw before. Settlement that is because of ejecta, so this is material that is ejected right next to the foundation of the building. And then shear induced settlement, which they performed more than 1,300 numerical analysis to estimate. And the way that their methodology performs versus data from centrifuge testing is shown in this graph. So you can see that there is some variability, but it does give a prediction. The slope is 1 to 2. Even more recently, we had a semi-empirical probabilistic settlement prediction methodology by Bullock et al. So there they had a very large number of numerical analyses, more than 63,000. Some of these numerical analyses were calibrated in terms of settlement prediction versus centrifuge tests. And they did a statistical correlation model that led to these probabilistic methodologies. And once they got these results, they compared them to a database of case studies. And they ended up having to shift this probabilistic framework to fit a bit better the case studies. So this is the final result. And you can see in this log-log space the observed versus the predicted settlement. Right, and if we go to rotation, as you saw in the pictures before, we also get a lot of rotation for these structures, which can be very significant because after the earthquake, there's not much that you can do. You might have to demolish, but there hasn't been that much about rotation. So recently there was again a semi-empirical probabilistic methodology proposed again by Bullock. So they took the same analysis that they had for settlement. This time they adjusted them with a reduced number of centrifuges and case studies where they had rotation data, and this is the residuals that they get for rotation. And there was another methodology recently by myself and Professor Madabusi that is based on centrifuge tests. So we proposed an empirical rotational stiffness degradation curve, and that was based on 14 centrifuge earthquake events, and it's normalized in a way that applies for different depths of layer and weight of structure and factors of safety. This degradation curve can then be used in simplified methodologies to predict settlement. This is an example of an iterative equivalent linear methodology. And this is how it performs for 70 different centrifuge events performed in other centers. Right, so we saw there what is available. Now we come to the question that hopefully we will try to answer, which is we have these simplified displacement predictions, but how reliable are they? What sort of margin can we take for them? And the main question is, do they capture the mechanics of the problem so that if we know that they capture the mechanics, we can trust that they will behave in a way that is more reliable, even when we have cases that have not been strictly validated against centrifuge tests, for example. So what are the deformation mechanisms that govern the generation of displacement? So in order to answer that, let's see a bit about the methodology we might use. We have, first of all, case studies. Now, these are excellent because they come from actual earthquakes, but they offer an image of what's happening after the earthquake. And often we don't have good data for the soil profile, the actual excitation, the details of the building. And in any case, we just have a snapshot of what happened at the end of the earthquake. So it's difficult to know what is the mechanism that led to that. Numerical modeling can give us deformation mechanisms, but what we produce will depend a lot on the constitutive model that we use, whether drainage can be modeled accurately, whether soil structure interaction and the interface there can be modeled accurately. So without good validation, it's not something that we can go to directly. And that brings us to centrifuge testing, which is what we used. So in a centrifuge test, we can accurately reproduce the stress-strain response that we get in reality. If we perform viscosity scaling, we can reproduce the drainage that happens during the earthquake. We can reproduce the soil structure interaction, and we can get detailed co-seismic and post-seismic time histories. So in terms of deriving or observing what the mechanisms are, centrifuge testing is a very good option. This is a picture of the Turner beam centrifuge in Cambridge where these experiments were performed. It's about 10 meters in diameter, and this is a photograph of one of the experiments before it was tested. So you'll see there is a soil layer somewhere in there and a camera somewhere close by. Let's have a look at the cross-section of the models that were examined and that will be presented today. So in all cases, we have a layer of loose, homogeneous Houston sand, which is a liquefiable sand that is fully saturated. In all cases, we use the viscous fluid so that we would be able to get drainage modeled accurately during the earthquake. We have a structure that is behaving during the earthquakes as a rigid body. So we sort of simplify the problem. We just focus on what's happening in the soil. And we tested for each depth of layer two structures, one light structure that has 50 kPa of bearing pressure and a heavier structure that has 100 kPa of bearing pressure. And in all cases, we used a container that had a window so that we could have a camera that could record what is happening in this cross-section. So in all of these cases, the problem is a plane strain problem. So this is a strip foundation. And yeah, we examined three normalized B over dl ratios. So B is the width of the structure and dl is the depth of the liquefiable layer. So let's see some of the results that we got from these tests. Right. So here are the results for the deep layer. So what's maybe worth looking here is on the top window, we have settlement, time history. The red line is the heavy structure and the blue line is the light structure. So here the heavy structure settles more than the light one. In terms of rotation, the blue line, again, is the light structure. What that does is that the amplitude of rotation is reducing as the earthquake is advancing, whereas for the heavy one, the amplitude of rotation is increasing. And what's maybe worth noting is that for the settlement, the sort of more faint lines there, their displacement measurement close to the boundary. So in both of these cases, these are going upwards, which signifies that the deformation mechanisms we got were very large. So it's possible that we have boundary effects for this deep layer. And this is something that Kostas will address in his talk. So if we go to the more shallow layer, there we see that in terms of settlement, we get the same response for both heavy and light structure. So here the bearing pressure of the structure does not seem to be as important. And in terms of rotation, we have a slightly different starting rotation, but again, in both cases, we have a large rotation amplitude, so we get a rocking type of response for both of them. And when we go to the very shallow layer, again, a similar type of response here for the heavy foundation. The earthquake stops a bit earlier, but up to then we get similar type of response both for settlement and rotation. Now, let's see how the simplified methodologies perform for these experiments. If we take the 1D methodologies, then they perform well for the deep layer and the light structure. So there, the settlement is not that different from what we would get just for a layer. But they've performed poorly for everything else. So these are really not reliable. And we will go into why a bit later. If we look at this graph, we already knew from the case histories from Berthelot that for thinner layers, this does not perform that well. And if I plot on top of that the data points from these experiments and from other recent or relatively recent centrifuge experiments, we see that, again, this is not very reliable. It seems to favor volumetric mechanisms so that it will give larger settlements when we go to deeper layers, which is not necessarily the case. If we go to the updated methodologies based on case histories all proposed by Berthelot, then this consistently gives a good upper bound. Often it's a factor of 2 of what we actually got, but it is nevertheless an upper bound compared to what we actually got. Right, so then if we move on to methodologies based on numerical simulations, then, well, you'll have to wait for the next talk to see a bit more about that. So the idea for the numerical simulations is that what we will get will depend on the reliability of the numerical simulations. So when we go to numerical simulations, what we will aim to show, what Kostas will aim to show is what are the strengths and the weaknesses when we do numerical modeling of this phenomenon. Also, what should we ask for validation? Is a comparison with the settlement of the structure enough, or should we be looking at a more strict validation, looking at more aspects of what happens in an experiment? The bottom line is, again, can we capture the mechanics of the problem? So can we capture the mechanisms that produce this displacement? So what are the mechanisms actually that produce displacements? In these experiments, because we had a camera taking pictures of what was happening, we're able to have results where this is an example where we will see the behavior of a deep layer, light structure on it, 50 kPa of bearing pressure. The contours are excess pore water pressure. And on the right-hand side, you have a settlement rotation graph. And you will see as I played the velocity contours. So what you will see happening here is that in this case, we have low excess pore water pressures under the foundation, and we have a bulb of increased effective stress, right, where the bearing pressure of the foundation is applied, that moves along with the structure, and it displaces the surrounding soil. So the soil around it and underneath it. And so the settlement is generated as this bulb of soil that moves along with the structure, displaces the surrounding soil. Right. If we go to a shallow layer, and again, the same sort of 50 kPa bearing pressure structure, you'll see that here we have quite a different behavior. So in this case, again, well, we have low excess pore water pressures in places where the soil is sheared, so where we get dilation. We have now the area of increased effective stress under the structure that reaches the base of the layer. It creates a column that transmits acceleration to the structure. So the structure responds by rocking. And as the structure is rocking, we have a soil structure interaction mechanism that displaces soil from under the edges of the foundation. That's how the settlement is mostly produced. So you have a very different mechanism. Right, let's see at what happened for all of these experiments at the end of the earthquake. So this is, these are displacement vectors for the ultimate, for the displacement that was accumulated during the whole earthquake. On the left column, you have a light structure. On the right column, a heavy structure. And you have the very shallow, the shallow, and the deep layer. Notice that for the deep layer, the y-axis starts at 5. The base of the layer was at 0. So as we saw a bit during the videos, what we observed is that there is an area under the foundation that maintains increased effective stress. This area moves along with the foundation and displaces the surrounding soil. So this is sort of a simplified version of the mechanism that drives settlement. In the thinner layers, this area reaches the base of the layer, and so the structure sort of stands on this column of soil of increased strength and develops a rocking response that displaces soil from under its edges. If we switch to horizontal displacement contours, here it becomes more clear, if I superpose again these areas, that in the deep layers we have the maximum horizontal displacement at a greater depth. So in the light structure under this bulb, and in the heavy structure this comes a bit higher up as the structure responds more with more rotation. And in the case of the shallow layers, in all the cases actually we have maximum horizontal displacement from under the edges, and this is what drives settlement. We can also produce shear strain graphs, and here you'll see that for the deep layers in this bulb of increased effective stress, we don't really get much shearing. So again, the settlement is produced as the surrounding soil is moved around. So you could think about it as this bulb of increased strength driving itself inside the softened soil. Whereas in the shallow layers, we get maximum shear strains around the edges of the foundation. This is what primarily drives settlement. In all cases, the mechanism that drives settlement are primarily shear dominated. So it's not a surprise that the volumetric 1D predictions do not perform well. It's mostly shear strain that drives displacement. Now, another interesting point I will just touch on very briefly is the evolution of the mechanism. So this is an example from the shallow layer and a light structure. Sorry, this way. So this is the evolution of excess pore water pressure close to the base under the foundation. So here you'll see that very quickly we build up pore pressure, but this pore pressure gradually dissipates during the earthquake. So we have co-seismic drainage that drives down the excess pore water pressure. We have the opposite picture under the edges of the foundation, where initially we don't have that high excess pore water pressure because there's a lot of dilation happening in that zone that is sheared a lot. But eventually, because the soil surrounding it is fully liquefied, we have co-seismic drainage. So there's water going into this area that is gradually increasing the excess pore water pressure. So what happens is deep under the foundation, gradually the effective stress increases, and under the edges of the foundation, the excess pore water, the effective stress, gradually goes down. So let's see what that does for the mechanisms. So initially, this is just the second half cycle. We have a very large mechanism. Now, remember that the soil deep under the foundation here is quite soft now because the pressures go up very quickly, and there we don't have that much softening. So it's a very large shear mechanism that engulfs mostly the whole area under the foundation. If you go somewhere in the middle of the earthquake, the excess pore water pressure under the center of the foundation, I'm not sure why you don't see my mouse now, well, has dissipated. So this area is not participating that much, so we don't have much shear strain deep under the foundation, whereas we have more shearing under the edge of the foundation where the soil has softened, and this is even more exacerbated at the end of the earthquake, where, again, because of co-seismic drainage, we have less shearing in the column under the foundation and much more shearing next to it, where the soil has now softened. So this is something worth keeping in mind that maybe we need to also take into account. So wrapping up, the 1D methodologies and also the first empirical graph of settlement versus width of the foundation are unreliable for structural settlement. And this is because settlement is actually primarily driven by shear mechanisms. So anything that gives too much weight to volumetric induced settlement is not going to work that well. However, the updated methodology of Berthelot does seem to give a good upper bound in all cases. So if that's what we're after, then maybe this is a good methodology to use. Then when we go to the deformation mechanisms under shallow foundations, what we observed is that for deep layers, we have a quotation marks, soil-soil interaction mechanisms. That means that we have an area of soil of increased effective stress that moves and displaces the liquefied or softened soil around it, and that's what drives settlement. Whereas when we go to shallow layers, we have a much more soil structure interaction mechanism, where it's the structure rocking and displacing soil from under its edges that is driving settlement. Final point, we do get co-seismic drainage, so this is maybe something we should look at a bit more, and that leads to an evolution of the deformation mechanisms that we get, which can change from the beginning to the end of an earthquake. Now some implications and hopefully a link to Kostas' talk. When it comes to numerical modeling, often what we do for validation is that we check acceleration and settlement for the structure. However, even if we do perform well for that, we need to question whether we can capture accurately the pore pressure generation under the structure, how well we do for the rotation of the structure, and also maybe more broadly, can we capture the deformation mechanisms, which would give us more confidence when we then extrapolate and we do parametric analysis. Final point is, do we get drainage right? So Kostas will hopefully answer something on the first part of the numerical modeling, and he will focus on the strengths and weaknesses of what we can do in the sort of state of the art of numerical modeling. However, there are some questions about physical modeling. You saw that in the deep layers, we got some boundary effects. So can we use numerical modeling to investigate how significant that effect is, and maybe have that as a guidance for how to design physical modeling experiments? So these are the references that were mentioned in this presentation. And with that, I would like to thank you for your attention. And I think Fiona wanted questions at the end of the session. So if you have any questions, please keep them until the end. Thank you very much. Right.
So, hello also from me. I would like to welcome you to my presentation on the numerical modeling of structures with shallow footings on liquefiable layers. The work that I will present today was mainly conducted during my PhD in ETH of Zurich under the supervision of Professor Anastasopoulos and Professor Adamidis. So I will start directly with the context of my presentation, which includes the main objectives of our research. Then I will describe the numerical modeling, the calibration, and the validation process. And finally, I will present some results, some indicative results regarding the boundary effects in centrifuge testing. So the main objective of my thesis was to gain insight into the key mechanisms that govern the response of the problem, and to identify the efficacy of numerical modeling to reproduce such response. But in order to cope with a high complexity of the problem, we conducted a fully coupled effective stress time history analysis, which were performed in the fine difference code FLAG2D, employing the constitutive model PM for sand. And models like PM for sand, in general, are capable to model the complicated stress-strain response of liquefiable soil, but contain a large number of parameters demanding for careful calibration. That's why we have to be very careful when we use these models. That's why we conducted a broad set of element tests. We try to characterize the behavior of host on sand, and we use this element test to conduct a robust calibration. After that, we use 6 experiments. The experiments that Orestis described and conducted during his PhD in Cambridge. So we have 6 structures with surface foundations founded on the layers of host on sand with different liquefiable layers, depths of liquefiable layers, and different bedding pressures. So with this way, we can check our methodology versus different stress paths and different characteristics. You see also, Orestis mentioned before that we will also test our methodology versus displacement fields. So this was the reason particle image velocimetry was used to extract displacement fields. And this was the reason that the tests were conducted in a rigid box and not in a laminar or an ESB box and flexible box. That's why in all the tests you can see that there is a ductile material at the lateral boundaries to allow for some deformability and also to absorb some of the incident waves. We'll see what are the implications of this. So first some words about the PM4 sand, which is stress ratio controlled, critical state compatible bounding surface plasticity model. It's based on the model of DM04 of Professor Dafalias and Manjari, incorporating, though, a lot of modifications. And among them, the critical state is expressed now in terms of the critical state ratio CR. We can see also that the fabric parameter and the evolution of fabric depends on the plastic shear than the plastic shear strain than plastic volumetric strain. And also the model, the dilation of the bounding surface doesn't depend on the load angles, excuse me. And the model is also but the model is also formulated in two dimensions, so it's a 2D model. Okay. So the model comprises 6 primary parameters, among them the apparent relative density, the shear modulus coefficient, which controls the elastic response of the model, a contraction rate parameter, and by adjusting the contraction rate parameter, we can adjust the cyclic stress resistance of the solid that we model, the atmospheric pressure, and 2 other flag parameters. This is the primary parameters. We also have 21 secondary parameters in the model, which can have the preset values. And in this study, for 10 parameters were calibrated versus element tests and measurements. And for 3 other parameters, we conducted sensitivity analysis. So with this, and in order to calibrate all these parameters, as I said, we tried to characterize the sand. So we conducted in the Institute for Geotechnical Engineering in ETH of Zurich, limiting void ratio tests, drained and undrained triaxial tests, bender element tests on triaxial cells, drained direct single shear tests, and constant volume direct single shear tests. Some words about this. So through triaxial test, the critical state parameters of the host of sand were determined. And on the chart on the left, you can see the critical state line with the parameters of the default parameters of PM4 sand. And with red line is the update line based on our measurements. Then, for the determination of the small strain stiffness of the sand, we conduct bender element tests on triaxial cells. On the left, you can see the experimental setup that we used, the bender elements on the triaxial cells. And on the right, you can see our experimental measurements in terms of normalized stiffness versus the void ratio. And we also compare our results with the analytical expression of Azeiteiro, who also conducted similar tests on host on sand. We see that his expression with red, it's a good approximation of host on sand. And for this reason, we can use his expression for the calibration so far. Because I didn't mention, but we try and we want to have a consistent calibration, a protocol that always we use the same procedure, and we don't want to do fine tunes for every test in order to have better results. So this is a good thing here. So for the determination of the liquefaction potential, we conducted constant volume simple shear tests in the NGI apparatus in ETH of Zurich. We also actually refurbished a bit the apparatus with new screw jack actuators, new LVDTs, electronic ones, and with a new control system, and now allowing for fully automated control in strain and load loading. On the right side, you can see our experimental results for 3 densities. And in terms of triggering liquefaction criterion, we considered the point where the shear strain is equal with 3.75% in single amplitude. And then we feed the results also in an exponential equation, the one on the top. So based on this, we can have the cyclic stress resistance of this sand for any void ratio, for any load cycles. And this will be used also for model calibration. Sorry. It's a bit slow, sorry. Yes. So finally, we conducted drain direct simple shear tests to estimate also the drain response of the sand. Here, what you see on the left side is with dots, it's experimental results for 3 initial vertical stresses in terms of shear modulus degradation and damping ratio versus the strain amplitude, the cycle strain amplitude, and we compare the results with the analytical expression of Sebastian for the shear modulus degradation, constructing this analytical expression based on the initial shear modulus that we have measured in the bender elements. So we see that this hopefully, or not hopefully actually, it's good news that our sand, it happens to follow the Sebastian Zank. It doesn't happen this way with every sand. I mean that we are very close. Okay, and then we compare also the predictions of pin for sand for the same characteristics. Probably here it seems that the pin for sand has already been calibrated versus the Sebastian Zank. This is good news for us. It means that based on our measurements, we have a good response in the drain, in terms of drain response too, for our case. Now, after the characterization of Houston sand, we can proceed to the calibration of the model. As I said, we want to have a procedure that is controlled and consistent every time. So, what we did for the limiting void ratios were estimated from limiting void ratio tests, and the QR and critical friction angle, critical state friction angle from compression triaxial test. Then the relative density for each test and the initial shear modulus were calculated directly as functions of void ratio. The permeability was calculated directly for every test as a function of void ratio, the viscosity, and the temperature of each test, of each centrifuge test, from the Kozenian-Karman equation and based on the measurements of Adamidis et al. For Houston sand. And then after this, we have the CSR curve for every test. Every different test was calculated based on the equation that was developed from the constant volume simple CR test as a function of the void ratio. And the last parameter to be calibrated is the contraction rate parameter. This is a parameter of the model to fine-tune and to adjust the resistance. So here we saw the first persisting problem, actually, the first limitation during calibration that we couldn't alter is that with the adjustment of this parameter, we can move the CSR curve to the right or to the left, but we cannot change the inclination. And this is like a persistent characterization of the model. You cannot change this, at least with the parameters that we used. We didn't find a way to change. So to cope with this difficulty, we actually calibrate the model for some numbers of interest, 0 to 20 for us here, which is like the important for the problem that we study. The second persistent limitation was the increased, actually, the reduced pore water pressure predicted by the model during the first cycles. So if we compare the stress paths, we see that consistently during the test and during the first cycles, we have like a greater loss of effective stress than the model. This is also something that it's inherent, it's in the model, and you will see, we can see that maybe it has some implication for the modeling of the tests, this thing here. So let's continue to the numerical modeling of the centrifuge test. So here is a typical model for a centrifuge test. We conducted fully coupled effective stress analysis in FLAC. The pin for sand calibration was based mainly on the void ratio of each centrifuge test. And in the absence of more information, the ductile material was modeled as elastic, with its elastic properties to be adopted from Popescu and Prevron. We will see that also this modeling will have significant implications later. Then the structure was designed to behave as rigid. That's why we modeled also as linear elastic rigid with an interface allowing for sliding and detachment. We didn't model the box, the rigid box, but the input was applied in terms of velocity in all the peripheral nodes of the model. And finally, taking into account the programming capabilities of FLAC, all the simulations were constructed fully automatically and parametrically. Okay. And now we can move to some results. So this is the prediction for the pore pressure in the free field, we compare always against 6 tests with the same calibration process, specifically here for 3 points in most of the experiments. So in the columns, you can see that we have the tests with different depths of liquefiable layers, and in the rows, we have tests with different bearing pressure. On top is the 50 kilopascal, low is the 100 kilopascal. In general, we can say that we have more or less a good prediction based on all this uncertainty for this test, for the free field. However, the situation is not the same below the structure. Here is the same chart, but now we compare the pore pressure predictions below the structures every time for many points. So we see that more or less for the deep layers, we can have more or less a good prediction. It's not bad. However, for the intermediate and the shallow layers, we don't have a good prediction, both in terms of the initial build-up and in terms of the subsequent dissipation or drainage during the analysis. So we can say that this could be attributed maybe to the inability of the model, not only this, but also maybe to the inability of the model to accurately predict the abrupt drop of effective stress during the first loading cycles. And also for the drainage, already we can think that the model without a cap surface has an inherent inability to model correctly the volumetric strain during loading. The model is actually more capable to capture CR failure and not volumetric failure. So this can be also a reason that we have this inability to model these things here. Moving to the settlement rotational response, here we compare the settlement rotational response for the 6 experiments, which is also predicted with non-negligible discrepancies. We see that in general, and we knew that it's easier to predict settlement than rotation. We see that in terms of settlement, the final settlement is predicted reasonably well for the 6 experiments, except the heavy experiment in the intermediate deep layer. For the experiment 8, actually, here one, we have reasons to believe that this discrepancy has to do with a parasitic vertical component of input motion that was recorded during the centrifuge test and was not modeled here. So actually, when we modeled also the vertical component, the settlement is closer. What has happened here? The model also captures the model in general doesn't capture the evolution of settlements and actually the maximum rotation, the dynamic rotation, but it has managed to capture in terms of behavior, but not in terms of amplitude, the progressive evolution and actually the reduced amplitude, the progressive reduced amplitude of rotation in this test. Probably this we can think that maybe we have captured also a different mechanism between different tests if we have different response. So also in terms of final rotation, but not dynamic rotation, the results are not bad. So here we compare also the experiments in terms of contours of shear strain at the end of the shaking. We see that for all the tests, we have the centrifuge model test and the numerical prediction for the 50 kilopascal stress and the 100 kilopascal stress, vertical stress. So we see that with the exception of the 6th experiment, the shearing observed directly below the foundation is predicted. Also, the numerical simulation captures the limit amplitude of shearing below the foundation in experiment 4 due to the lower rocking rotation that was predicted before. Also, we see that in both tests, in both deep tests, 4 and 5, we see that we have significant boundary effects, and this can be seen by the failure mechanism that actually reaches the daxil material, and also with the shear strains that are concentrated. Actually, what I didn't say is that here at the shaft starts the daxil material. So everything that you see here is sand, and after this is the daxil material. So we see that we have significant pressure on daxil. And also, just to remind that we have modeled Daxil as linear elastic, which probably has significant implications, especially for the deep layers, where we see that these boundary effects are significant. Also, we see that in this mechanism here, in the fourth experiment, we have captured the deep mechanism, but here we see a deeper, a shallower mechanism, failure mechanism for this test. Let's see. So, obviously, Daxil material is not elastic, but it has some nonlinearities, but we didn't have any information about this, so we had to model like this. Here, in order to check this hypothesis of the nonlinearity, we conducted a small parametric, a simple parametric and sensitivity analysis. So we changed the elasticity modulus of Daxil from double to half of the initial estimate. And we run again the analysis. And what we see that for the deep layers, we have a great Daxil material has a great influence in the final settlement. And actually, we see that when you adopt the lower value, you better estimate the settlement. And not only this, but more importantly, the elasticity modulus of Daxil affects also the mechanism. And till now, we were thinking that we used the constitutive model with 29 parameters to model the sand. And actually, we see that the simplest material here actually changes a lot of results. But this happens only for the deep layers, okay, where the mechanism reaches the Daxil material. And what we see that, again, if we, let's say, there is some nonlinearity, and let's say that the elasticity modulus drop, we see that we can capture much better both the settlement and the failure mechanism. We're much closer to the reality. So, to sum up, we saw that so far we conducted a robust validation versus 6 centrifuge tests, taking into account displacement fields, and with a calibration that was mainly based on the void ratio. We saw that our model can capture adequately well the final settlement and the final rotation. Actually, this numerical model outperformed all the simplified methodologies that Orestis referred before for settlement prediction. We see still that beta lot acts in most of the cases as an upper bound solution. We see also that maybe also the analysis, for example, of Bullock that was based on 63,000 analysis. It's not that they have a clear superiority over some other method, at least for the cases here that we model here. So the analysis outperformed all the simplified methodologies for the settlement prediction, but the advanced analysis was outperformed by the simplified method of Orestis and his professor for the rotation prediction. Then we saw that the analysis cannot capture well the settlement evolution and the dynamic rotation. And also we saw that the Daxil response is very important. It has to model in more detail. It has to be characterized. And also it has to be taken into account during the interpretation of the centrifuge test, because it seems that it changes the response or affects the response. So, influence from this, after that, we conducted a parametric study in order to study the influence of the container type, the distance of the lantern boundaries, and the depth of the lantern boundaries in the settlement, and the maximum structural rotation and acceleration of centrifuge tests. So, what we did, we considered 3 cases. We considered that this experiment could have been conducted in a laminar container, in a Daxil boundaries, and even in a rigid container in a case of a laboratory that doesn't have this equipment. What will happen and how this will affect the results. This result based on the numerical predictions that we know that they are not perfect, but they have the limitations, but more or less we know that some things we can trust in. So here I present the results in terms of the settlement, of the final settlements, and we can see, all the results are presented normalized with the normalized versus the distance of the lateral boundaries for 3 depths of liquefiable layer, and they are normalized with the value of the laminar container for the maximum distance considering that this is closer to the reality. So consider that reality is the value of laminar box, which we know that is the best approximation of the problem for the maximum distance. What we see that from a laminar container, already for a distance equal to 1, depth of liquefiable layer, we can model accurately the settlement. Then we see that the Daxel inclusions help a lot, and actually after 6 steps, we see that we don't have any fluctuation, and also before 6, the fluctuations are not so high, are about 10%. We also see that all the experiments that we analyzed lies in this case, in this region. So in all the experiments, actually, we have some boundary effects based on the analysis, but it was not more than 5% or 10%, these boundaries, at least for the settlement, and based on the analysis. Now, for the rigid container, what we see that also, again, we need the a distance of 6 depths, but the fluctuation before this distance are much higher. But at least we can see that even with a rigid container, you can model at least the settlement based on these results without a laminar container, which maybe cost 80,000 or 60,000, I don't know. So, in terms of rotations, the same graphs, but now for the rotation. What we see again, first of all, the structure, like the differences are higher, sorry. And in the laminar container, we have the best results. The Daxel boundaries have worse results than the laminar container, but after a distance of 6 to 8, we see that we have some convergence. And for the rigid container, we have the worst results. And we see also that it's not clear if we have some convergence or not in the settlement, in the rotation. It seems that it always changes. So in order to study this a bit better, we conduct some other analysis, and we will focus now on these charts. So what we see here, we see the time histories of the acceleration of every point at the surface of 2 tests with lateral distances equal to 4 depths and 5 depths. 4 is the red, 5 depths is the black. So for all the containers, so for every container, we see two simulations actually, one with distance of lateral boundaries equal to 4 depths and equal to 5 depths. It starts, the graph in the horizontal axis starts from the edge of the foundation, and all the points below the foundation are not presented for better visualization. So what we see, and it's important, in the case of the laminar container, we have the shear wave arriving at the same time, 6.46, at the edge of the foundation in both analyses. And then we see that this is transmitted to the outer edges of the box, and this makes sense because, as Orestis said, below the foundation we have higher initial higher stresses. This means stiffer response, increased shear velocity. So it starts from the foundation and it's transmitted to the shallow, to the edge of the foundation. Now, in the rigid container, we have the opposite. What we have the shear wave coming from the edges of the foundation. Sorry, from the edges of the box, going to the edges of the foundation. And what is important here, we see why this happening. This happening because the box is always much stiffer than the soil. And we see here that no matter what, always, these waves will arrive to the foundation with a time lag. Even if you use distances of 30, 40, 50, always this 40 will be different than 41, so we will have a time lag. And this maybe is the reason why we have this greater difference in rotation and we don't have convergence. And in the Daxel boundaries, we have a similar response. We see that first of all, this is important, comes at the same time to the edges of the foundation here, is transmitted to the edges of the model, but also it comes also from the Daxel in this case. So Daxel doesn't manage to totally filter out the acceleration, and also we have some incident acceleration from the box. And to sum up, this brings me to the conclusion of my presentation. So initially, we saw that in order to pursue robust calibration, a broad set of element tests was conducted. So we conducted a strict validation versus 6 experiments. We take into account also the deformation mechanism. We used a consistent calibration mainly based on the void ratio. This process revealed the strong points and the limitations of the numerical technique and the constitutive model, setting the point for future improvements and work in this field. We saw that the final settlement and the rotation were captured, but not the rate of settlement and the dynamic rotation. Also, the key aspects of the failure mechanism were produced. The behavior we saw regarding the Daxel, we saw that the behavior of Daxel has to be modeled in more detail in order to have reliable results. And we saw also that with the numerical tool, we studied the boundary effects in centrifuge experiments, and we were able also to draw some conclusions and maybe to provide some tips for a better design and interpretation of future centrifuge model tests. And with this, I would like to welcome you to thank you for your attention.
Thank you, Orestis and Konstantinos, for your presentations. Do you want to both sit down, and you can have the comfort of your seat for the Q&A. Valentina, do you want to grab a microphone? Is that okay? Brilliant. So if anybody in the audience at the ICE has a question, if you raise your hand, and Valentina can bring you the microphone. For everyone who's online, if you have a question, do type it in the chat online. I have an iPad here so I can see the questions, and I'll read them out for our speakers. So yeah, I'll just thank again Orestis and Konstantinos for your very clear presentation of what is a very complex topic. So thank you. So first question from the audience, if you can introduce yourself and then the question.
Orestis, thank you for the interesting presentation. One short question regarding the co-seismic drainage that you mentioned. Is this a generally observed trend or a function of the permeability of the materials you tested and perhaps the input excitation?
Yes, thank you for the question. So it will depend on how much of it you get will depend on the permeability of the sand that you have. But I think that generally for a sand and the typical duration of an earthquake, you're almost always likely to get some co-seismic drainage. And actually, I think in every centrifuge test that I have seen, where you have a sand being examined, even if it's just a layer and you don't have a structure that is making things more complicated, you always get significant co-seismic settlement. Often this is comparable or higher than the post-seismic settlement. It depends a bit on the sand, but just the fact that you get settlement during the earthquake, if you just consider a layer of sand, that means that you do have some drainage happening during the earthquake. When you have a structure, then this will affect what your structure is doing, but I think that some co-seismic drainage always exists. So maybe we should shift a bit our idea of liquefaction as an undrained event. I think you always do get some drainage happening.
Thanks a lot. Can I ask something more about the Kostas this time?
Go ahead.
Okay. Apologies for the monopoly. Kostas, again, thanks a lot for the interesting presentation. Regarding the calibration, which was based on the relative density or void ratio, what range of relative densities did you consider? Only for looser materials, more susceptible to liquefaction, or also denser, let's say 80%, 90% relative density?
Look, so the calibration, actually, the process that we did, sorry, is it open? Yes. So for the specific calibration, we tried to model the experiments of Orestis, which happens to be for liquefaction. So it has been tested. It happens for loose materials. But we have different densities, and also the experiment 6, I think it's almost 64% in terms of relative density. Now, this concept, maybe it has not been tested for a dense material, but at least for the procedure, it will be the same. If you have a denser material, the same equation will calculate a different coefficient for elastic shear modulus. Then for the equation for the cycle stress resistance, you will calculate an initial curve, another curve, and then you will have a stronger material. The permeability will be calculated on the void ratio. So this is the good of being, and then of course it will come. Again, I understand that we will have a more dilative material, and then it has to do with the constitutive model if it can capture the response of this dilative material. But also at 90%, maybe you don't have liquefaction, and then everything is easier.
Yeah, but I think that the experiments, they were for a range. So yes, what Kostas presented was a function of voids ratio. So if you have a different voids ratio, the calibration sort of campaign would still cover that. Yeah.
Clear, many thanks. The rest, I hope for drinks later to be asked. So.
Yeah.
Okay, is anyone else in the audience here at the IC got a question? Brilliant.
Hello, Guillermo Aldama from Jacobs. Thank you for the very interesting presentation. And this is a question more like to open a discussion as well for both, because building up on what already was discussed is the input motions that you use for the calibration, how that will affect, because on the centrifuge test, from what I saw, you're using sinusoidal signals, and real ground motions will have a range of frequency distributions and other intensity measures, including the duration of the ground motion. How do you think that will affect your models and the validation that you are doing in the centrifuge? And also, something interesting that you were discussing about the boundary effects on the centrifuge. In real life as well, what you will expect is some reflections and refractions from nearby buildings or basin effects. All of that will also influence what you're doing. Obviously, I'm generalizing a lot here to the work that you are doing, but I think it's very interesting to discuss also those points.
You want to?
Yeah. So yes, thank you very much. So the first part of the question was about the frequency content or the input motion. So in what we did, we wanted actually to go with something that is constant frequency sinusoidal motion, so that we would be able to focus a bit more on the mechanisms, and so that we could compare half cycles, let's say in the beginning compared to the mid or the end of the earthquake, so that we could see the evolution in a way that did not include, let's say, very big pulse in the beginning versus something different in the end. So of course, the frequency content is important. When you have liquefaction, it's maybe less important than in other problems, especially for deep layers. You might have some of these frequency being filtered out if you get liquefaction. If you have more shallow layers, then obviously there's a lot of the acceleration being transmitted through this higher effective stress column under the structure to the structure itself. So then it would be important, as it is in any case where you have an earthquake. However, I think that for the stage or the information that we were trying to analyze, it would make it very difficult to draw conclusions on mechanisms, because we would be comparing very different things somehow. We wouldn't be able to track the evolution of a mechanism, because then that would depend also what the input motion is doing. Yeah, so I don't know if I've covered. So yes, I think it's important. I think for deeper layers, it's maybe a bit less important, because I think some of the higher frequencies might get filtered out if you have liquefaction. Now going to the second part, I think you're spot on. You're absolutely right. And most of the failures we get are in urban environments, and there we have a lot of neighboring structures. This was actually a big part of Kostas's PhD. We didn't present anything on it today, but yeah, maybe he can tell some things about it. But very important problem, yes.
Yes. So before this, I will say also something about the earthquake, and correctly, an earthquake has, if we like use this methodology for different earthquakes, which have different number of loading cycles, and I present you these results with a model that cannot capture the cycle stress resistance over a greater amount of cycles. Then we should revisit these results and we should think what we're doing. Maybe we have a problem because I ran on earthquake with 2 cycles. In the 2 cycles, I overestimate the resistance. Then I have another earthquake with 4, 5 significant loading cycles. Then I underestimate the resistance. Then we have problem. Like I cannot do this. I say I validate the model, and then I like start doing 60, 50, 100,000 analysis and like producing results. This is the one. Now for the second thing, in terms of about the boundaries, in terms of reflection, wave reflections, I think the problem will not be very big because actually this soil, when it's liquefied, it will filter everything. In terms of structure, soil structure interaction, what Orestis said, it's very important because actually never the structure will be so alone, isolated somewhere. And actually we try to see everything here in detail. But we have seen that even structure, soil structure interaction exists even for distances between the buildings of 6, 7 foundation widths, which, like in an area, in a city area, it's very difficult to find. And it changed a lot the response. So yes, you're totally right that we should also consider structural soil structure interaction. Thank you.
Yeah, thank you both for your responses there. I think we'll now quickly jump to some questions that we're getting online. So confirmation that the live stream has been working well. So the first question we have is from Ziggy Lukowski from Arup. So the question is, thanks very much for an interesting presentation. Professor Adamidis, how would the deformation mechanisms you have shown change if the real overturning loads from the building were included in the centrifuge tests?
So if the real overturning loads?
Yes.
So, yeah, just to clarify, in the videos I showed, there was a box that was outlined that was moving, but that was not just a slab foundation. We had an actual structure that had an aspect ratio. So that building did get P delta effects and overturning loads as an actual structure with that aspect ratio would. So I think these were, if I'm understanding the question right, I think these were included in the centrifuge test. It was not just a slab placed directly on the layer. There was a height to that structure. The center of mass of the structure was higher than the foundation.
And I guess a question, I guess for myself, building on that, what would you have, I guess, seen differently if you'd had an asymmetric structure? Just in terms of real life structures are never perfectly symmetric. Yes. How would that then maybe change what you'd seen in?
So I don't know if you observed, but all of them accumulated rotation in one direction. I think that had to do with the direction of the first loading cycle. So any asymmetry would cause an accumulation of rotation. So in reality, if you have a structure that's a bit more loaded on one side, that would definitely lead to an accumulation of rotation. I think that would be the most significant aspect of what would change in the response. Yeah,
just not enough time in a PhD to cover everything. Brilliant, thank you. So the next question, just a response from Ziggy says, thanks for the clarification.
Oh, okay, thank you.
Sorry, I'm just getting up to speed with the iPad and the questions as well at the same time. So the next question we have is from Stavroula Conta from Imperial College London. She's saying, thank you very much, both excellent work and presentations. Several liquefaction case studies refer to stratigraphies which include both liquefiable and non-liquefiable, so low permeability layers. I was wondering whether you could comment on the impact of this system response of interlayered deposits on the settlement predictions. To what extent is this captured by existing methodologies?
Okay, so if I thank you very much for the question. Thank you very much for the question to Stavroula. So this is a very important aspect of liquefaction response, that in reality we do have layers and it's a systems response. So it will depend. In this case, we had the structure sitting on top of directly on top of a liquefiable layer. There's much in the literature about having a crust on top of this liquefiable layer. So you have a layer that is maybe non-permeable just below the structure, and this does affect the response. Now, everything will depend on sort of the relative permeability of these layers and the relative thickness. So it's not necessarily a very straightforward response. What is certain about this question is that, yes, our current methodologies do not account for it, especially the simplified methodologies. Some of the methodologies based on numerical calculations, such as the one by Bullock, there you can have a thin crust that is non-liquefiable, underlain by a liquefiable layer, and below, again, a different layer. So there, at least in the numerical simulations, that was included. So this is possible to get some estimations about what would happen. In terms of liquefaction susceptibility, the methodologies we currently have certainly do not account for that. And you saw that we have drainage happening during the earthquake. This is an important aspect of the response. When you have a layer deposit, if you have differences in permeability, you will get zones of water inflow or outflow, and this will have a changed liquefaction resistance. So you might get estimations that are not necessarily realistic, and Stavroul actually has an excellent paper on that from a negative, from a false negative prediction from Christchurch. So yes, absolutely, that is an important aspect. Now, when we go to foundation, which is what we studied, it's more difficult to tell. It will depend a lot on the relative the relative thickness of these layers and the relative permeability. There are some studies from, I'm sure everybody in the field of liquefaction will know about the Niigata cases, that were some of the cases from '64 that jump-started research into this area, that showed that maybe we had a thin, less permeable layer at the top of a liquefiable layer, where we had a zone of water inflow that might have caused sort of a surface with low strength, which could have caused a lot of the failures that we saw in Niigata. So yes, also in reality, that is a real issue. Yeah.
Great, thank you, Orestis. I'll carry on for the time being with a couple more questions that we've been getting online, and then come back to the audience here if there's still any more questions. So the next question we have online is from Domenico Gaudio from Sapienza University of Rome. He said, first, thank you for your interesting presentation. Just wondering if you have some explanation for not needing to calibrate the constitutive model parameters against the free field centrifuge results. From the literature, it usually results that element calibration is not enough, but in your case, element testing provided a wonderful simulation of centrifuge results.
Okay, suppose for me. So, it's okay. So actually, okay, we didn't calibrate versus centrifuge, we calibrated versus element tests, but we didn't have excellent results. So we didn't capture the free field, but we didn't capture the pore water pressure below the structure. We didn't capture the rotation. We didn't capture the settlement of rotation. We didn't capture the evolution of settlement. But for me, it's like this is important, because when you don't capture something, you go there and you see why you don't capture. Then if you have calibrated only versus on the element test, you see the element test, and you see what you try to connect them, and then you can draw a conclusion and say, this is because of this is because of the other. Now, if I calibrate versus another centrifuge test, if I understand correctly the question.
I think the question was more about the free fields. We did capture what's happening far away from the structure.
Yes, without calibrating versus centrifuge test.
So the question was, just wondering if you have some explanation for not needing to calibrate the constitutive model parameters against the free field centrifuge results. From the literature, it usually results that element calibration is not enough, but in your case, element testing provided a wonderful simulation of the centrifuge results.
I don't have any explanation. To speak the truth, I don't know if you need to do this. I tend to say no, because I have seen Class A predictions of centrifuge tests where they capture the free field settlements, the free field for water pressure, without calibrated versus tests. Also, in our case, this happened. So I don't know. For our case, element tests were enough. Maybe we're lucky.
Okay, so one more question that we have from online, which is from Pak Chi from Geotechnical Consulting Group. The question is, how much do you need to lower the bearing pressure until you start to see a shift in overall displacement response, i.e. from shearing governed, as presented here, to volumetric strain governed, as per 1D free field analysis? Do equivalent free field centrifuge tests show mainly volumetric response?
So yes, thank you for the question. In the experiments that we did and the simulations that we did, in all cases, the displacement was primarily shear driven. So even in the case of the light structure in a very deep layer, there the 1D predictions were not bad, but again we observed the shear mechanism that was more important. In this case, we had a bulb of stiffer soil sort of driving itself inside the liquefied material. So I would personally advise against using 1D methodologies in general when we're looking at structures. They might work for very light structures in very deep layers, but I think for most realistic cases, probably they would be unreliable. And I think there was a second part of the question that I'm forgetting now.
Do equivalent free field centrifuge tests show mainly volumetric response?
Well, if it's a free field test, then it has to be a 1D problem. So all of the settlement that we do get, I think would be volumetric, yes. And we do observe in centrifuge testing very significant amount of co-seismic settlements, comparable or in cases even larger than the post-seismic settlement. So in a conventional view of liquefaction where we anticipate that it's close to an undrained event and most of the settlement will happen afterwards, that's not necessarily what we're observing in centrifuge experiments, yeah.
Brilliant, thank you. Okay, I'll go for another round of questions from the audience here. Has anyone got a question they'd like to ask our speakers? No more hands raised here. And at the moment, no more questions online. So I'll just give people just one moment. If anyone's got anything they'd like to raise or ask, then please do. So no, I think take that as the end of our presentation. So first of all, I'd like to thank Konstantinos and Orestis for their brilliant presentations. So let's give them a round of applause, everyone. Thank you.
Thank you very much for inviting us.
And thank you for coming. It's been a brilliant evening. So 2 quick announcements before we leave. The first one is that the next SecEd event will be taking place on Wednesday, the 24th of November, which will be here at the ICE at 6 p.m. It's on V simulators, cutting edge facilities for human factors research in relation to vibration serviceability for structures by Professor James Brownjohn and Dr. Anthony Darby. So we hope to see many of you here next month. And the final point is, for everyone that's here, I'm sure there's a few of us that are keen to go for a drink, and so please do loiter and we'll group up and go for a drink. So thank you everyone for joining. Thanks to everyone online and for everyone here at the IC. And yeah, on behalf of the SecEd Young Members Subcommittee, thank you for joining today's event. Thank you.